Hello, welcome back. This is Calc 1 by Dr. Oz. We are in the second video of the series of two on the indeterminate forms and L'Hopital's rule. And in the first video, we talked about limits that produce indeterminate forms, and we had a head intro to the L'Hopital's rule and how to apply that, but we have gone through only a few indeterminate forms and the corresponding examples for that. So now I plan to continue with more examples to sort of make this indeterminate forms with the application of the L'Hopital's rule more solid in your mind. As I said, we talked about 0 over 0 or infinity over infinity type indeterminate forms, but there are other forms like 0 times infinity, 1 to the infinity, and infinity to the power of 0, and 0 to the power of 0, and obviously infinity minus infinity type indeterminate forms. Just one thing that you should realize in the series of examples here, that all of these forms would lead to 0 times infinity, but turns out that the limits exist, and in one case it's 1, in the other case it's 2, and in this case it's 0, and in another case the limit value is infinity. So you can actually see that each case has to be treated carefully, and as you see that 1 over x here tends to 0 as x approaches infinity. So you have 0 times infinity form here, same as here, 0 times infinity, and this is like 1 over e to the infinity, which is 0 times infinity, same as this one. Okay, so replacing the roles of x and e to the x would not change much of the form 0 times infinity, but it does change the limit value. So in this case, while x is going to go to infinity slower than e to the x, so the entire limit is going to tend to 0. And since, again, as I said, e to the x goes to infinity faster than x, so this limit is going to tend to infinity. So we got to be very careful when it comes to 0 times infinity type indeterminate forms. In general, what we do is to convert 0 times infinity forms to infinity over infinity, or 0 over 0 form, so we can actually use the advantage of the L'Hopital's rule. Because, again, for you to be able to apply the L'Hopital's rule, you either have 0 over 0 or infinity over infinity type indeterminate forms. And without converting this form into either this or that one, you can't really utilize the L'Hopital's rule. And here's an example of an indeterminate form, 0 times infinity. So let's check this out. So you have e to the x, which is in fact 1 over e to the x, when you look at the reciprocal, and you have radical x as x approaches infinity. So this bottom approaches infinity, so that this whole term approaches 0, and radical infinity is infinity, so this whole thing is of the form 0 times infinity. So to be able to handle this problem, we have to convert this problem, this limit, into either like 0 over 0, 0 over 0, or infinity over infinity. And now I'm just going to rewrite this expression as radical x divided by e to the x, because this form, as I said, this e to the minus x is equal to 1 over e to the x. So now, as x approaches infinity, I know that this term approaches infinity as well as this term. So now I have infinity over infinity type indeterminate form. So in this regard, I can go ahead and use the L'Hopital's rule, which essentially says that take the derivative of the top and take the derivative of the bottom. The bottom is easier because e to the x has the derivative e to the x. And radical x, if I convert that into the power form, it would have the derivative of 1/2 x to the power of negative 1/2. But if you simplify that form, so writing that as a reciprocal, you have 1 over 2 radical x e to the x. So now I have like one full fraction coming out of this. And as x approaches infinity, so I know that this term, both of these terms approach infinity, so the bottom approaches infinity. and the top is approaching 1 because it's a constant term. So this whole thing is behaving like 1 over infinity. So that implies that this limit is in fact equal to 0. Okay. All right. So is this limit, because I converted this 0 times infinity type indeterminate form to infinity over infinity type indeterminate form, so that I was able to use the L'Hopital's rule, and then that turns out to be the limit value 0. So is the very first limit. All right, we can graph the function and check the behavior of the function as x approaches infinity. So here we go. If you graph this function all the way, starting from somewhere along the 0, and if I change the x coordinates here, let me in fact do that real quick. I'm going to change the x coordinates to, let's say, 1000 from 10. And as you see that the corresponding values tend to, I can play with this. So as you see that we're approaching all the way to 0. Okay. In fact, I can also play with this value here. So let me just make this 100. So this way we can see that dash. So if I run the simulation, so if you go in this direction, if you go in the positive direction, as you see, then the corresponding values tend to 0, because this axis is 0. See, this is going along 0. So again, graphing helps, and I totally recommend you to graph the functions before even you start hitting the road. Once you have a calculator, obviously. If the calculator is allowed to be used, why don't you use it? All right, in the next example, I'm going to consider other special forms, 1 to the infinity, infinity to the 0, and 0 over 0. These are very special forms, and you have to know how to attack solving these limit problems. And here is one example where you have the indeterminate form 1 to the power of infinity, and we can just really check that as x approaches infinity. So 1 over x tends to 0, and then this whole thing acts like 1 to the power of infinity. So the strategy I'm going to apply here is applicable to the forms I just mentioned here, other forms. So here you start calling this as like y. Okay, your goal is to determine what y is, right? Because that's what the question is asking, but I just label it as y. Okay, and then I take ln of y in the next step. Okay, so ln of natural log of, in other words, both sides of the equation. And something that we know earlier, that natural logarithmic function is continuous. So I can sort of like interchange the limit and the ln operation here. So I can interchange, so I can put the limit out, and I can check the limit of x times ln of 1 over x. And remember that the original expression was ln of 1 plus 1 over x to the power of x, but using the property of ln, that I can sort of like put this x in front of ln, so I can rewrite that ln of 1 plus 1 over x. Okay. And now let's check what kind of limiting behavior we have here. So as x approaches infinity, so this term goes to infinity, and this term goes to 0. So you're talking about infinity times ln1, and ln1 is 0. So you're talking about 0 times infinity of the form. So by applying the trick of taking the ln of both sides and interchanging the limit and ln, so I converted this indeterminate form into infinity times 0 or 0 times infinity form. And from the previous example, we learned how to convert this form into either like infinity over infinity or 0 over 0. So here the infinity term is coming out of this, and then this is the one taking us to 0. So why don't we write this as 0 over 0 so that I can flip this guy over down. So I can rewrite this expression as ln of 1 plus 1 over x divided by 1 over x. So I put the reciprocal of x down here so that when you flip it over, you still have x times ln 1 plus 1 over x. But this time, as x approaches 0, this term goes to 0 as well as this term. So now I have 0 over 0 type indeterminate form. All right, so what I'm going to do next is, since this is 0 over 0, I can apply the L'Hopital's rule. I'll take the derivative of the top and the derivative of the bottom. All right, let's do it. We know how to take the derivative of ln. It's the derivative of the inner side divided by itself. So 1 plus 1 over x prime divided by 1 plus 1 over x. That takes care of the derivative of the top. And the bottom is x to the minus 1. By using the power rule, the derivative is minus x to the power of negative 2, which is negative 1 over x squared. And I'm going to use the same strategy here. So this is equivalent to negative 1 over x squared divided by 1 plus 1 over x divided by negative 1 over x squared. Okay? So we got to simplify this expression. So why don't we flip this guy over as minus x squared over 1. Okay? All right, so well, these guys are inverses of each other. When you multiply them, it's going to be 1, right? So let me just continue from here, that as limit as x approaches infinity, the limit of this whole expression here is down to the limit of 1 over 1 plus 1 over x. Because when you cancel out these terms, you have just 1 left, right? So now the limit expression is 1 over 1 plus 1 over x. So let's pass the limit to see if we got rid of 0 over 0 type indeterminate form. Yes, we did. In fact, 1 over x tends to 0, and then the whole thing tends to 1 over 1 plus 0, which is exactly equal to 1. Going back to the original form, this limit is found to be 1. Okay, but as you see that this is the value of ln y. So then I solve this equation for y, and we know how to solve it from pre-calculus. Y equals e to the power of 1 because ln comes with base e. So e to the power of 1 is equal to y, and y is exactly equal to e. And who is this guy? Well, this is the value of the original limit, which is equal to the limit of 1 plus 1 over x to the power of x as x approaches infinity. That converges to e. And e is a number, by the way, close to 2.71. And here is the graph of this function 1 plus 1 over x to the power of x. As you see that when you move in this direction, the corresponding function values get closer and closer to e. So this line is the horizontal line, y equals e. So the corresponding orange values, as you see, approach y equals e. As I said, graphical proof is always nicer to support your answer. All right, the next thing that we're going to discuss is about how we can use the L'Hopital's rule for sided limits. And we have an example here that we have 0 over 0 type indeterminate form, and then we are approaching 0 from the right, so this is sided limit. And we have sine x to the power of x, and we can visually verify where this limit tends to. Sine 0, when you're on the right of 0, is approaching 0, 0 to the power of 0 type indeterminate form, as you see, because x approaches 0. And sine 0 is almost 0 when you're on the right of 0. Okay. And we're going to apply the same trick because we have 0 over 0, 0 to the power of 0 type indeterminate form. Why don't we call this guy y? And then we take the ln of both sides. So ln of y is equal to ln of the limit. And since ln is a continuous function for positive inputs, I can interchange the limit and the ln, positions of limit and ln. So this becomes ln of sine x to the power of x, and using the property of ln, we get down to the limit ln x times ln sine x. Okay. So now let's pass the limit again. When we approach 0 from the right, this approaches 0. And remember that sine 0 approaches 0, but ln 0 blows up to infinity, so this term approaches infinity. So we have one of the indeterminate forms that we discussed earlier, 0 times infinity. And now we have to convert this to either 0 over 0 or infinity over infinity. And different from the previous example, why don't we convert this limit infinity over infinity? So this term is already going to infinity and this term is going to 0. I'm just going to consider x and its reciprocal. So in other words, I'm going to write this as ln of sine x divided by 1 over x. This way, this term is going to converge to infinity, and ln of 0, this is in fact minus infinity, but that's okay, converges to minus infinity. So you have infinity over infinity type indeterminate form, and this is where we are allowed to use the L'Hopital's rule. So here I can go ahead and start taking the derivative of the top and the bottom separately. And the bottom one, once you write this as x to the power of -1, and if you use the power rule, you have -1 over x squared. And the derivative of the top is the derivative of the inner function divided by itself. So sine has the derivative cosine, cosine divided by sine x. So let's just simplify this. Okay, so this is negative x squared times, this is cotangent x. Well, this form didn't really help a lot because when x approaches 0, this term approaches 0 and cotangent 0 blows up. This is still of the form 0 times infinity. So I'm going to rewrite this expression. Okay, I'm going to take the reciprocals of each term. Okay, so this one is going to be 1 over x squared. And let's see, I'm going to put the x squared to the top, and then the reciprocal of cotangent is tangent. So I'm going to put the tangent down, okay, together with the minus sign here. Okay, so this time tangent 0 approaches 0 once x's are on the right of 0, and then this term approaches 0 as well. So now I have another 0 over 0 type indeterminate form. And why don't we apply the L'Hopital's rule again? So the derivative of the top is -2x, and the derivative of tan is secant squared x. And now let's pass the limit again to see if we got rid of 0 over 0. So the top goes to 0, and the bottom goes to secant squared of 0. If you use your calculator, secant squared of 0 is 1. So that's good news because now the limit is 0 over 1, which is exactly equal to 0. All right, so I can go back and conclude that this limit is exactly equal to 0. If ln y is equal to 0, y is equal to e to the 0, which is 1. So this turns out that y is exactly equal to 1. And right now you can pause the video and graph sine x to the power of x, and let's see what you're going to have. All right, you should have a graph like this, and right now what I'm going to do is that I'm going to get closer and closer to 0 and to see that the limit value tends to 1. So there we go, I'm getting closer and closer to 0. Let me just slow it down a little bit. As you see that the corresponding values get closer and closer to 0. Okay, so as you see that starting from here, when I walk to the left, getting closer to 0 for x, the corresponding function values tend to 1, as you see. Okay. All right, the last example of this video is a different form, infinity minus infinity. And we have an example for that. So still we have the sided limit, as you see, and we're still using the power of L'Hopital's rule for sided limits. But let's see why we have infinity minus infinity. So x approaches 1 from the right, so this term is going to approach 0 from the right, so it's 0 plus. And then this is already 0 plus, so you will have infinity minus infinity here. Okay, so one of the ways to handle this problem is just to combine these two fractions and write it as one fraction with the hope of getting 0 over 0 or infinity over infinity type indeterminate form. So for that reason, I'm going to find a common denominator here and merge these two fractions into one. So here I'm going to multiply both top and the bottom by x minus 1, and here by ln x, so that I have x minus 1 minus ln x with the common denominator x minus 1 ln x. Okay, so now let's pass the limit again. So x approaches 1 from the right, so this term approaches 0, as well as this term, because ln 1 is 0. So the top is approaching 0. So this term approaches 0, ln 1 approaches 0, so bottom is approaching 0. So we successfully converted infinity minus infinity type indeterminate form to 0 over 0 type indeterminate form. So once you have this form, we have the right to use the L'Hopital's rule, and the next step, I'm going to use the L'Hopital's rule. All right, I just rewrote that limit here to save some space. All right, let's apply the L'Hopital's rule. So I'm going to take the derivative of the top, which is 1 minus 1 over x. I'm going to take the derivative of the bottom. So that's the product rule, okay? So ln x as the derivative of 1 over x times x minus 1 plus ln x times 1. So that's just ln x. So at this moment, still I have like this term and this full chunk here. So why don't we convert them to full fractions? So the top term can be rewritten as x over x minus 1 over x, so that I can combine these two into one fraction. Okay, so it becomes x minus 1 over x. And then this one, I'm going to put a 1 here. The common denominator in the bottom is x. So this is x minus 1 plus x ln x divided by x. So here, denominators are the same, just watch out. So now I have a fraction in the bottom. I'm going to flip that over, okay? So you have x minus 1 over x times x over x minus 1 x ln x. Okay. Here the x's divide out. So in the next step, I have the same limit as x approaches 1 from the right. At the top, I have x minus 1, and in the bottom, I have x minus 1 plus x ln x. Okay. In the next step, I'm going to check the limit. I'm going to pass the limit, in fact. Okay, so x minus 1 converges to 0 if x approaches 1. So 1 minus 1 is 0. So the bottom here, this one converges to 0, and as well as 1 times 0, that's 0. So we still have 0 over 0. We couldn't sort of like avoid 0 over 0, but no problem. We're going to apply the L'Hopital's rule one more time, and I'm going to take the derivative of the top and the bottom in the next step. All right, I just rewrote the same expression here. Well, the derivative of the top is 1, and the derivative of the bottom is 1 plus the derivative of this term, which is the product rule. So ln x plus x times 1 over x. Okay, let's simplify that. It's 1 over, this is already 1 because x times 1 over x is 1. So it's 2 plus ln x. Okay. So now let's pass the limits. Well, the top is constant, so it converges to 1. The bottom is 2 plus ln 1, which is in fact 2, since ln 1 is 0. So as you see that this limit is just 1 over 2, which is an awesome news. So I can go back and conclude here that this limit is equal to 1/2. And as I told you earlier, graphing is always awesome. So now we're approaching 1 from the right. As you see that if I approach 1 from the right, the corresponding values approach all the way to 1/2. I can in fact graph 1/2 just for you to see. Okay, so essentially when I get down to 1 from the right, the corresponding values get closer and closer to 0.5. Okay. And if you want to use the other technique, you can still do that. You can use the table of sample values. As you see that as you get closer to 1, the corresponding values approach 0.5, which is in fact 1/2. All right, let me finish this video by a quick remark here. Just realize that L'Hopital's rule is only applied to 0 over 0 or infinity over infinity type indeterminate forms. Like for example, this use of L'Hopital's rule is incorrect because as x approaches here, as x approaches 0 here, e to the 0 approaches 1, and this is already 0. This is not 0 over 0 or infinity over infinity. In fact, this is 1 over 0. As you see that falsely, we took the derivative of the top and the bottom separately, and we got a wrong result of 1, which in fact is not the limit value for this expression. So that's an incorrect application of the L'Hopital's rule. And here are some exercises for you to go through as applications of L'Hopital's rule. In one case, you have 0 over 0, infinity over infinity, and 0 times infinity. Please, after watching this video, go ahead and then try to attack these problems. And let me see if I have another example here. Yes, I do. I have the limit of x to the power of 1 over x, which is of the form infinity to the power of 0. So please do this exercise as well. And finally, I have a few more of the forms infinity minus infinity. Please also check those problems. It may take time because sometimes the algebraic manipulations are not that easy. So take your time, go slowly, try to digest every single step, and please do those exercises after you watch this video. All right, so this is the end of the video. I'll see you in another video. Bye.